Welcome to this comprehensive video on understanding the curved surface area of a cone. Today we're going to break down this important geometric concept step by step, making it crystal clear and easy to understand. First, what exactly is a cone? A cone is a three-dimensional geometric shape that has a circular base and comes to a single point at the top, which we call the apex. The top point is called the apex, and the bottom is a circular base. You can think of familiar objects like ice cream cones or traffic cones as real-world examples. Now here's the key concept. The curved surface area refers specifically to the area of the curved part of the cone. This does not include the circular base, only the slanted sides that connect the base to the apex. Think of it this way. If you were to paint only the slanted sides of a cone, the curved surface area would tell you exactly how much paint you need. The base would remain unpainted. In this video, we'll explore the key concepts you need to understand, learn the curved surface area formula, see how it's derived, work through detailed examples, and discover real-world applications. By the end, you'll have a complete understanding of this important geometric concept. So grab your notebook and get ready to master the curved surface area of a cone. This is going to be an engaging and thorough exploration that will build your confidence with this geometric concept. Before we can work with the curved surface area formula, we need to understand three fundamental measurements of a cone. These measurements are the foundation for all cone calculations. First, let's examine the radius. The radius, denoted by the letter r, is the distance from the center of the circular base to any point on the edge of the base. The radius is always measured horizontally across the base of the cone. This measurement is crucial because it appears in both the curved surface area and total surface area formulas. Next, we have the height of the cone. The height, represented by h, is the perpendicular distance from the apex down to the center of the base. Notice that the height is always perpendicular to the base. This means it forms a right angle with the base of the cone. The height is used primarily in volume calculations. Now comes the most important measurement for curved surface area, the slant height. The slant height, denoted by L, is the distance from any point on the edge of the base to the apex, measured along the surface of the cone. This is crucial to understand. The slant height is not the same as the height. The slant height follows the slanted surface of the cone, while the height goes straight down perpendicular to the base. These three measurements are related by the Pythagorean theorem. If you look at the cone from the side, you can see that the radius, height, and slant height form a right triangle. This gives us the relationship L squared equals h squared plus r squared. This means if you know any two of these measurements, you can always calculate the third. Understanding these three measurements and their relationships is essential. The radius and slant height are the key measurements we'll use in the curved surface area formula, while the height is primarily used for volume calculations. Now we arrive at the heart of our topic, the curved surface area formula. This elegant mathematical expression will allow us to calculate the surface area of any cone's curved surface. The formula CSA equals πrl contains four key components. CSA stands for curved surface area. This is what we're calculating. Pi is the mathematical constant approximately equal to 3.14159. The letter r represents the radius of the cone's circular base, and L represents the slant height of the cone. Now let's visualize what this formula represents using a three-dimensional cone. Here we see a cone with its key measurements. The radius r extends from the center of the base to its edge. The slant height L is the distance from any point on the base's edge to the apex of the cone. The curved surface area formula comes from a fascinating geometric insight. If we could unwrap the curved surface of this cone, it would form a sector of a circle. When unwrapped, the cone's curved surface becomes a sector of a circle. The radius of this sector equals the slant height L of our original cone. The arc length of this sector equals the circumference of the cone's base, which is 2 pi r. This unwrapping reveals why our formula works. The area of this sector is exactly the curved surface area of our cone. So our formula CSA equals πrl gives us the area of the cone's curved surface. This formula multiplies pi by the radius and slant height, capturing the relationship between the cone's dimensions and its surface area. With this formula in hand, we're ready to see how it's derived and then apply it to solve problems. Now we're going to discover where the curved surface area formula comes from through a fascinating visual approach. We'll literally unwrap a cone to see its true shape. Imagine we have a sharp knife and we make a single straight cut from the base of the cone all the way up to the apex, following the slant height. This cut will allow us to unfold the curved surface. When we carefully unfold this cut cone and lay it flat, something remarkable happens. The curved surface transforms into a sector of a circle, like a slice of pie. This sector has two crucial measurements. First, the radius of this sector equals the slant height of our original cone. Second, the arc length of this sector equals the circumference of the cone's base. Now comes the mathematical insight. We need to find what fraction of a complete circle this sector represents, then use that to calculate its area. If we had a complete circle with radius L, its total area would be pi times L squared. But our sector is only a fraction of this complete circle. The fraction of the circle that our sector represents is the arc length divided by the full circumference. The arc length is 2 pi r, and the full circumference is 2 pi L. We can simplify this fraction. The 2 pi terms cancel out, leaving us with simply r divided by L. Now we can find the area of our sector. It equals this fraction times the area of the full circle. And there we have it. The curved surface area of a cone is pi rl. This visual derivation shows us exactly why this formula works. The cone's curved surface is literally a sector of a circle with radius L and arc length 2 pi r. Now we'll work through our first example problem. We need to find the curved surface area of a cone when we're given the radius and slant height. Here's our cone with the given measurements. The radius of the base is 5 centimeters, shown in orange. The slant height from the apex to the edge of the base is 12 centimeters, shown in green. Now let's set up our solution. We'll use the curved surface area formula and substitute our known values step by step. First, let's clearly identify what we know and what we need to find. We're given the radius as 5 centimeters and the slant height as 12 centimeters. We need to find the curved surface area. Step 1, we start with the curved surface area formula. CSA equals pi times r times L, where r is the radius and L is the slant height. Step 2, now we substitute our known values. We replace r with 5 and L with 12. So CSA equals pi times 5 times 12. Step 3, let's calculate this step by step. First, we multiply 5 times 12, which gives us 60. So we have CSA equals 60 pi square centimeters. Step 4, to get a numerical answer, we use pi approximately equal to 3.14159. So CSA equals 60 times 3.14159, which gives us 188.5 square centimeters. This is very important. Always remember to include the correct units in your final answer. Since we're measuring area, our units are square centimeters. So our final answer is 188.5 square centimeters. This represents the area of the curved surface of the cone, not including the circular base. Notice how we used the formula systematically and showed each step clearly. Now we'll work through our second example problem. This time, we need to find the slant height when we're given the curved surface area and radius of a cone. Here's our problem setup. We're given that the curved surface area is 220 square centimeters and the radius is 7 centimeters. We need to find the slant height, which we'll call L. Let me draw a diagram to visualize this problem. Here's our cone with radius 7 centimeters. The curved surface area of 220 square centimeters refers to the area of the curved side surface, and we need to find the slant height L. Step 1, we start with our curved surface area formula. CSA equals pi times r times L. Step 2, to solve for L, we need to isolate it on one side of the equation. We divide both sides by pi r, giving us L equals CSA divided by pi r. Step 3, now we substitute our known values. CSA is 220 and r is 7, so we have L equals 220 divided by pi times 7. Step 4, let's calculate this step by step. Pi times 7 equals approximately 21.99. Then 220 divided by 21.99 equals approximately 10.0 centimeters. Perfect. We found that the slant height is 10 centimeters. Let me update our diagram to show this result. We can verify our answer by substituting back into the original formula. Pi times 7 times 10 equals approximately 219.9 square centimeters, which matches our given curved surface area of 220. This confirms our answer is correct. This problem demonstrates how we can rearrange the curved surface area formula to find any unknown variable. The key is to isolate the variable we're looking for through algebraic manipulation, then substitute the known values and calculate carefully. Now that we understand how to calculate curved surface area, where do we actually use this knowledge in the real world? The CSA formula has many practical applications across different industries. In manufacturing, curved surface area calculations are essential for determining how much material is needed to create conical containers like funnels, hoppers, and storage vessels. Engineers use the curved surface area formula to calculate exactly how much sheet metal or plastic material they need to manufacture each container, minimizing waste and controlling costs. In architecture and construction, curved surface area calculations help determine the amount of roofing material needed for conical structures like tower roofs, silos, and decorative architectural elements. Architects and contractors calculate the curved surface area to determine how many square feet of shingles, metal roofing, or other materials they need to purchase for the project. The food industry relies heavily on curved surface area calculations, especially for designing and manufacturing ice cream cones, paper cups, and other conical food containers. Manufacturers calculate the curved surface area to determine how much wafer batter or paper material is needed to create each cone, ensuring consistent product quality and cost control. Even traffic safety equipment uses curved surface area calculations. Traffic cones require precise amounts of reflective material to ensure maximum visibility for driver safety. Safety engineers calculate the curved surface area to determine exactly how much reflective tape or coating is needed to cover each cone, ensuring optimal visibility while controlling manufacturing costs. As we can see, the curved surface area formula is not just an abstract mathematical concept. It has practical applications in manufacturing, architecture, food production, and safety engineering, helping professionals make accurate calculations for real-world projects. We've covered a lot of ground in this video about the curved surface area of a cone. Let me summarize the most important points you need to remember. The fundamental formula for curved surface area is CSA equals pi RL, where R is the radius of the base and L is the slant height of the cone. Here's a visual reminder of our cone with its key measurements. Remember that R is the radius and L is the slant height we use in our formula. First key point. Curved surface area specifically excludes the circular base of the cone. We're only calculating the area of the curved lateral surface. Second, always use the slant height L in your calculations, not the perpendicular height H. These are different measurements, and using the wrong one will give you an incorrect answer. Third, always include proper units in your final answer. Whether it's square centimeters, square meters, or any other unit of area, this is essential for a complete solution. Finally, carefully read each problem to determine if the slant height is given directly, or if you need to calculate it using the Pythagorean theorem from the height and radius. Now you have all the tools you need to solve curved surface area problems confidently. Practice with different examples to strengthen your understanding. If you found this video helpful, please give it a thumbs up and let me know in the comments. Your questions and feedback help me create better content for everyone. Don't forget to subscribe and hit the notification bell for more math tutorials. What topic would you like to see next? Let me know in the comments below and keep practicing.